we have seen two different matrix decompositions. The singular value decomposition and the QR decomposition. What I want to do in this video is demonstrate how both of these are useful for solving systems of equations. The fundamental problem in linear algebra is to solve the problem AX equals B. You have a fixed matrix A and a fixed matrix B, and you want to find the x that solves this linear system of equations. That's where it all begins. Now, of course, you'd say, well, perhaps A has an inverse. We can apply row operations to find A inverse, and then x is A inverse B. That's certainly true as far as it goes, but perhaps A inverse does not exist, but we still want a solution, say using some reduced row echelon form of A in the row operations, a pseudo-inverse. On the other hand, it turns out that this operation of doing row operations is not exactly numerically stable. If you have small errors in A or B, they can accumulate through this process of manipulation and division of the different rows, and very bad things can happen numerically, as we will see. So before we get into the numerical analysis details, what I want to do is demonstrate how these two decompositions, the singular value decomposition and the QR decomposition, can be used to help you solve a system of equations. So in each case, we're trying to solve AX equals B. And we don't want to use the inverse. Suppose we have a method to compute the SVD directly, and suppose we have a method to compute the QR decomposition directly. For instance, in the QR decomposition case, as you're seeing now, you can use the Gram-Schmidt process, or an improved version we'll see later. So if you can compute these two decompositions, then this problem becomes a lot easier. For example, in the SVD case, it becomes this. Now, that's not a very big change. A is U sigma V star, but this has an important meaning. Here's what we can do. Instead of solving to find A inverse, we can replace that inverting process with three very simple operations. And here's the process. Step 1. Write the vector, let's call it C, which is U star B. Again, that's just writing it down and doing matrix multiplication. Taking an adjoint or a transpose is essentially no computational work at all. You just keep track of the pluses and minuses in the complex numbers, and you flip the order of the matrix. There's no actual arithmetic going on other than the matrix multiplication here. Step 2, solve a system that I'll write this way: sigma y equals C. Now, sigma is essentially a diagonal matrix. So solving sigma y is simply dividing along the diagonal the n numbers. In fact, this is saying, right, that C is a multiple of y up to that division. So this is just arithmetic on n entries, if this is an n vector and an n vector and an n by n diagonal matrix. So that's easy. Step 3, well, now x is equal to Vy. This is multiplication again. We already have V written down, or rather V star, so take its conjugate transpose and multiply it by y. And you see if you do this sequence of 3 steps, what we've written is, well, x, so y is V star x, and sigma y is C, and sigma V star x is sigma y is C is U star B. So we've found x that solves U sigma V star equals x equals B, or AX equals B. So what we've done by doing the singular value decomposition is we've replaced this tedious process of row reduction with 3 very simple steps. Take a transpose or an adjoint, invert a diagonal matrix, and another transpose or adjoint. You can see that's a huge speed up of the operation as long as we can find u sigma and v from the beginning quickly. So we need an algorithm to do that. Okay, now in the QR decomposition case, it's fairly similar. So you start off by saying, well, suppose I had Q and R, I could write QRX equals B. Okay, so step 1, write C equals Q star B. Again, Q being unitary or orthogonal, its adjoint is its inverse. And then 2, solve Rx equals C. Now here's the point, R is upper triangular. So that means that this solving is by back substitution. So you can solve for the last variable, and then the second to last, and then the third to last, and so on. Back up the variables until you've found all of your x's. And therefore, what we have is Rx equals C, which is Q star B, and therefore QRX equals B, which is AX. So we've replaced finding the inverse of A with, again, taking the adjoint of a matrix, which is essentially free computationally, and doing a matrix multiplication, which is straightforward, involves no division, and then doing back substitution, which is quite direct and straightforward. So we can see that not only do these have interesting geometric meaning, they have important computational meaning. We are replacing a fairly complicated and intricate process, finding a matrix inverse by row reduction, where you have to make lots of decisions, check that certain minors are non-zero and so on, do pivoting, keeping track of lots of things and doing lots of division with one of these two simpler processes. So our goal then is to find a way to do either of these decompositions easily on its own, and then once we can do that decomposition, we can solve any linear system of equations by replacing it with a process like one of these.